ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the fifth lecture of Module 5 on Analysis and Design for Shear and Torsion. In this lecture, we shall study the design for shear. First, we shall study about the limit state of collapse for torsion provisions. We shall learn about the design of longitudinal reinforcement and then about the design of transverse reinforcement. The limit state of collapse for torsion. The design for the limit state of collapse for torsion is based on the Skewbending theory. For a beam subjected to simultaneous flexure and torsion, an equivalent ultimate bending moment at a section is calculated. Last time, when we discussed about the analysis for torsion, we learned that for the Skewbending theory, three modes of failure are defined at ultimate, and these modes of failure are based on a concept of a resultant moment which comes from the flexural moment and the torsional moment. Based on this concept, an expression of equivalent ultimate bending moment is developed for the design for torsion. The design for torsion involves the design of longitudinal reinforcement as well as the transverse reinforcement. This is very important, that the resistance to torsion comes from a truss action where the concrete struts, the longitudinal steel and the transverse reinforcement all take part in resisting the torsion. Hence, the design targets both the steel, longitudinal and transverse. For concrete, the design considers its capacity. The longitudinal reinforcement is designed based on the equivalent ultimate bending moment that is defined based on the Skewbending theory. The transverse reinforcement is designed based on the Skewbending theory and a total shear requirement. For the capacity of concrete to consider the simultaneous occurrence of flexural and torsional shears, an interaction between the two is considered. The equations in IS 1343-1980 are applicable for beams of the following sections: solid rectangular with D, which represents the depth, greater than B, which represents breadth. In case if a member has a larger breadth than the depth, then D will be equated to the larger breadth and B will be equated to the smaller depth. Hence, D is always larger than B in the expressions that we shall see. The expressions are also applicable to hollow rectangular sections where the thickness is greater than 1/4 of the breadth. That means the hollow rectangular sections should have adequate thickness for the resistance to torsion. And finally, the equations are also applicable to flange sections like T beams and I beams. These are the three types of sections for which the equations are applicable. For a solid rectangular section, D is larger than B. Similarly, for a hollow rectangular section, D is larger than B, and the thickness is greater than or equal to 1/4 of B. For flange sections, B has to be substituted by the breadth of the web for most of the expressions. The variables are thus: B is the breadth of the section, which is equal to BW for flange section. D is the total depth of the section. T is the thickness of the section for a hollow section. The average pre-stress in a section at the level of CGC is limited to 0.3 FCK. First, we are moving on to the design of longitudinal reinforcement. For the design of longitudinal reinforcement, there are three expressions of the equivalent ultimate bending moment for the three modes of failure. We had seen these three modes of failure in our last lecture, and those modes of failure are modeled by three expressions of the equivalent ultimate bending moment. The background of the codal provisions is given in a paper written by Professor Rangan and Hall. The title of the paper is Design of Prestressed Concrete Beams Subjected to Combined Bending, Shear and Torsion. It was published in the SCI journal, published by American Concrete Institute in March 1975. The volume number is 72 and the issue number is 3, and the pages are from 89 to 93. In the first mode of failure, there is an influence of the torsion in the bending, that the plane of failure is skewed with the axis of the beam. But the zone of compression and the tension remain similar to conventional flexure. This is modeled by an equivalent moment which creates compression in the same phase as that of the flexure, and it creates tension in the same phase as that of the flexure. The equivalent ultimate bending moment for mode 1 failure is denoted as ME1, and ME1 is equal to MU, which is the flexural moment at ultimate, plus MT. MT is the equivalent bending moment for the torsion at ultimate, and it is given as follows: MT is equal to TU, the torsion, times root over within bracket 1 plus 2D divided by B. First, we calculate the torsional demand at ultimate. From that, we are calculating an equivalent bending moment, and then we are adding that equivalent bending moment to the flexural moment to get the total equivalent bending moment for mode 1 failure. In this expression, mu is the applied bending moment at ultimate, mt is the additional equivalent bending moment for torsion, and Tu is the applied torsion at ultimate. Since the torsion generates tension in the reinforcement irrespective of the sign of mt is same as that of mu. Remember that whether the torsion acts clockwise about the axis or anti-clockwise about the axis, it always generates tension in the longitudinal steel. To account for this addition of stress due to torsion in the longitudinal steel, the sign of mt is taken as the same as that of mu, such that finally we have an increased demand in the longitudinal steel due to flexure and the torsion. For the mode 2 failure, the amount of torsion is significantly high, and this type of failure is seen for beams with thin webs. Here, the compression of concrete is at one side face and the tension is in the other opposite side face. To model this mode 2 failure, the equivalent bending moment is considered to act about a vertical axis, which creates compression in one side face and tension in the other side face. The notation used in the codal expression is Me3 for the mode 2 failure. The equivalent ultimate transverse bending moment for mode 2 failure is represented as Me3, and Me3 is equal to Mt, whose expression we have already seen, times 1 plus x1 divided by 2e whole square times 1 plus 2b divided by d divided by 1 plus 2d divided by b. This is the expression of the equivalent moment which acts about a vertical axis, creating compression in one side face and tension in the other side face. In this expression, E is equal to Tu divided by Vu, ratio of ultimate torsion and ultimate shear force at a section, and x1 is the smaller dimension of a closed stirrup. Thus, if we have the rectangular section, then x1 is the dimension of the closed stirrup which is smaller, y1 is the dimension which is larger. The transverse bending moment Me3 is considered when the numerical value of mu is less than mt. Me3 acts about a vertical axis. The second mode of failure is considered when the torsion is substantial, and that is judged by the consideration that when the numerical value of mu, the flexural moment, is less than the equivalent bending moment due to torsion mt, then we are checking for the second mode of failure, which is the transverse bending failure. And remember that Me3 is acting about a vertical axis to generate compression in one side face and tension in the opposite side face. The third mode of failure is generated when the torsion is substantial and the top steel is small. In that case, we may observe crushing in the bottom and substantial yielding in the top steel. In this sketch, we can observe that the compression is occurring at the bottom and tension is in the top, which is in an opposite sense to what is created by flexure. And here the modeling is done by a moment which generates bending in an opposite sense to that of the flexural moment. if the flexural moment is creating compression at the top, the equivalent bending moment for the mode 3 failure creates compression at the bottom. And this way we check the requirement of the steel at the top. The equivalent ultimate bending moment for mode 3 failure is denoted as ME2 in the code. ME2 is equal to MT minus MU. The expression of MT is same as for mode 1 failure given before, and the mode 2 failure is checked when the numerical value of mu is less than that of MT. ME2 acts in the opposite sense of that of mu. Just to summarize, that the third mode of failure is checked when the numerical value of mu, the flexural moment, is less than the equivalent moment due to torsion, which is denoted as MT. And then the total equivalent moment, which is ME2, acts in an opposite sense to that of mu. That is, if mu generates compression at the top, then ME2 will generate compression at the bottom, and thus we are designing for the steel which is under compression due to flexure, but may come under tension when both flexure and torsion are occurring together. The longitudinal reinforcement is designed for ME1 similar to the flexural reinforcement for a beam. When ME2 and ME3 are considered, longitudinal reinforcement is designed for these two moments also. Thus, the procedure is that when a beam is subjected to simultaneous flexure and torsion, we are designing for an equivalent ultimate moment ME1, which is larger than mu, to consider the effect of torsion, where we may also design for ME2 and ME3 if the moment due to torsion MT is numerically larger than mu. Thus, the essence of design of longitudinal reinforcement for a beam under combined flexure and torsion is that we have defined an equivalent moment which is larger than the flexural moment and acts in the same sense of the flexural moment. We may also define two other equivalent moments if the torsional moment is substantially high, one for the lateral bending and another for the negative bending, which is in the opposite sense of the bending due to the flexural moment. For a singly reinforced section, the amount of longitudinal reinforcement AS is solved from the following equation: 0.87 Fy times AS times D within bracket 1 minus Fy AS divided by Fck times Bd is equal to Me. This expression is available from our reinforced concrete design, and for a singly reinforced section which is under reinforced, the moment is the force in the steel times the lever arm, and from that we get this expression which can be solved to calculate the value of AS, the amount of longitudinal reinforcement. In this expression, ME is any one of ME1, ME2 or ME3. D is the effective depth of longitudinal reinforcement. Fy is the characteristic yield stress of longitudinal reinforcement. Fck is the characteristic compressive strength of concrete. And as I said, Me is one of Me1, Me2 and Me3. When we are substituting Me1, we are designing the bottom steel. When we are substituting Me2, then we are designing the steel in the side, and when we are substituting Me3, we are designing for the steel at the top. Hence, depending on the relative values of mu, the flexural moment, and mt, the equivalent moment due to torsion, we design for the longitudinal steel in the bottom, the side or the top. Next is the design for transverse reinforcement. For the design of transverse reinforcement, the capacities of concrete to resist the torsion and shear need to be determined. To consider the simultaneous occurrence of flexure and torsional shears, a linear interaction between the two is considered. What we had seen earlier in our shear design was that before we can design for the transverse reinforcement, we calculate what is the contribution of concrete to resist the shear. Similarly, when torsion is present, we calculate the capacity of concrete to resist the torsional shear and flexural shear simultaneously. Now, to consider the occurrence of these two types of shears simultaneously, an interaction equation is assumed. The capacity of concrete is to resist torsion is reduced from Tc, the capacity under pure torsion. Similarly, the capacity of concrete to resist shear is reduced from Vc, which is the capacity in absence of torsion. The meaning of interaction is that we can calculate an expression of the capacity of concrete under pure torsion. We can calculate an expression of concrete to resist shear in absence of torsion. These two capacities are represented by Tc and Vc respectively. Now, when both shear and torsion are occurring, the capacity of concrete to resist torsion will get reduced from Tc. Similarly, the capacity of concrete to resist shear will reduce from Vc. Next, we are developing the equation for the capacity of concrete under pure torsion, which will be represented as Tc. The capacity of concrete is determined based on the plastic theory for torsion. The capacity is equal to the torque generating the first torsional crack, which is represented as TCR. For a reinforced concrete beam, TCR is estimated by equating the maximum torsional shear stress, which is tau max, caused by TCR to the tensile strength of concrete, which is estimated as 0.2 root over FCK. The estimated tensile strength is less than that under direct tension because the full section does not plastify as assumed in the plastic theory. Thus, to get an expression for the torsional resistance of concrete, we refer to the plastic theory of the analysis of torsion. With that theory, we equate the expression of the maximum shear stress generated at the mid depth of the longer face to a tensile strength of concrete, which is given as 0.2 root over FCK. Now, this estimate of the tensile strength of concrete is lower than the direct tensile strength because in the plastic theory it is assumed that the full section is plastifying at failure, but whereas when concrete cracks, the full section does not plastify as assumed in the plastic theory. Hence, the tensile strength of concrete is reduced. The estimate of the cracking torque TCR for a rectangular section is given below. This expression is obtained from the plastic theory, and TCR is almost equal to 0.2 root over FCK times B squared D divided by 2 times 1 minus B divided by 3D, which when simplified gives TCR is equal to 0.1 times B square times D times within bracket 1 minus b divided by 3d times root over fck. This is the expression of the torque that causes the first crack in the concrete member. Now, the expression that we had seen was for a rectangular section. For a flange section, the section is treated as a compound section. A compound section is a summation of rectangular sections. The cracking torque is estimated as a summation of the capacities of the individual rectangular sections. Since the interaction between the rectangular sections is neglected in the summation, the estimate of the cracking torque is the lower bound estimate. To explain, let us see this idea of a compound section for a flange section. The following flange section is shown as a compound section of 5 rectangles. For an individual rectangle, the short side is B and the long side is D. Thus, in this flange section, we have divided it into 5 rectangles, 1 to 5. And for each individual rectangle, we are finding out the capacity which is given for a rectangular section. And then we sum up this capacity to get the TCR for the flange section. In doing this summation, we are not considering any interaction between these rectangles, and hence the summation is actually a lower bound of the true value of TCR. That is, whatever we calculate will always be lower than the actual value of TCR which can be observed from an experiment. The estimate of the cracking torque TCR for a compound section is as follows. TCR is equal to the summation for the individual rectangles of the 0.1 times b square d within bracket 1 minus b divided by 3d times root over fck. Thus, once we calculate the capacities of the individual rectangles, we can sum them up to get the total capacity for the compound section. Remember that the B and D values are for the individual rectangles. For a prestressed concrete beam, the strength of concrete is multiplied by the factor lambda p, which is a function of the average effective prestress, which is FCP. We had observed earlier that the effect of prestressing is to reduce the principal tensile strength that is developed at the mid depth of the longer side. Hence, the cracking torque is much higher, and even after cracking, the strength of the concrete is retained as the aggregate interlock is retained due to reduced crack width. Hence, in presence of prestressing force, the strength of concrete is increased by multiplying by a factor lambda p, which is a function of the amount of prestressing force at the level of CGC. Lambda p is given by the expression lambda p is equal to root over 1 plus 12 FCP divided by FCK. The value of FCP is taken as positive, that is, only the numeric value is considered. It can be observed that the strength increases with prestress. Thus, here we are taking into account the effect of the prestress in the strength of concrete. The cracking torque and the capacity of concrete to resist torsion, which is given as Tc, for a prestressed concrete beam is thus estimated as follows. Tc is equal to Tcr, which is equal to summation of 0.15 b squared d within bracket 1 minus b divided by 3d times lambda p, here lambda p takes account of the prestressing force, times root over FCK. This is the expression given in the code for the torsional strength of concrete under pure torsion and in presence of prestressing force. In this expression, B is the breadth of the individual rectangle in a compound section and D is the depth of the individual rectangle in a compound section. Next, we are finding out the capacity of concrete under shear. These expressions we had seen in the analysis for shear, and the same expressions we are revising once again. There are two expressions of the capacity of concrete for shear, one for an uncracked section, which is the amount of shear generating a web shear crack, and the second expression is for a cracked section, which is the amount of shear that converts a flexural crack to a flexure shear crack. The first expression is for an uncracked section. Vc is equal to Vc0 equal to 0.67 B times total depth T times root over Ft square plus 0.8 times Fcp times Ft. Vc0 is the shear causing web shear cracking at CGC. Ft is the tensile strength of concrete equal to 0.24 root over Fck. Note that this tensile value is larger than that we had used for the finding out the torsional strength of concrete. For cracked sections, Vc is equal to Vcr, which has two terms. The first term denotes the shear which converts a flexural crack to a flexure shear crack, and the second term is the shear which generates a flexure crack. Vc is equal to within bracket 1 minus 0.55 FPE divided by FPK, where FPE is the pre-stress in the tendon, times tau c times BD, and the second term is M0 times Vu divided by Mu. The strength of concrete need not be less than 0.1 BD root over FCK. Vcr is the shear corresponding to flexure shear cracking. The notations in the previous equation are as follows. FPE is the effective prestress in the tendon after all losses, and it should be less than or equal to 0.6 FPK, where FPK is the characteristic strength of prestressing steel. Tau c is the ultimate shear stress capacity of concrete obtained from table 6 of IS 1343-1980. It is given for values of AP divided by BD, where D is the depth of the CGS. This is the plot of the variation of tau c with the amount of prestressing steel. What we observe is that as the prestressing steel is increasing, the capacity of concrete to resist shear is also increasing, and this is explained by the fact that in presence of prestressing force, the aggregate interlock is, the cracking occurs at a higher load, and the resistance after cracking is retained because the aggregate interlock is retained and the zone of concrete under compression is larger. The dowel action is better in presence of prestressing force. Now, this values of tau c is given in the form of a table in IS 1343, whose graphical representation is shown in this graph. The other variables in these equations are d is the distance from the extreme compression fiber to the centroid of the tendons at the section considered. M0 is the moment initiating a flexural crack, which is estimated as 0.8 times FPT times I divided by Y, where FPT is the compressive stress in concrete at the level of CGS due to prestress only, I is the gross moment of inertia, Y is the depth of the CGS from CGC. The derivation of these two equations were covered under the design for shear. Mu is the moment due to ultimate loads at the design section, and shear Vu is the shear due to ultimate loads at the design section. Thus, given the expressions of Vc0 and Vcr, we can calculate Vc, which is the capacity of concrete to resist shear in absence of torsion. Now, we are reducing the capacity of concrete to resist torsion and shear when both of them acts together. This is done by the help of an interaction equation. A linear interaction of the shear and torsion capacities of concrete is considered. This figure shows that the ultimate shear Vu is normalized with the capacity of concrete to resist shear in absence of torsion. This variable is in the x-axis. In the y-axis, the ultimate torsion is normalized with respect to the capacity of concrete to resist torsion under pure torsion. This variable is plotted in the y-axis. A straight line is joined from the value of 1, where Tu is equal to Tc, to a value where Vu is equal to Vc. Thus, the two extreme points corresponds to the cases of pure torsion and shear in absence of torsion. When both of them occurs, the capacity is reduced based along this straight line, and this is a linear interaction. Thus, if the demand is somewhere within this straight line in the green area, then the section will be safe. If the demand lies outside the interaction line, then it will be unsafe. The interaction equation is given as follows: Tu divided by Tc plus Vu divided by Vc is equal to 1. This is a linear interaction equation. It is the plot of the straight line that joins the 2 points in the axis as we had seen in the graph. Now, from this linear interaction, we are calculating the capacity of concrete to resist torsion and shear when both torsion and shear are acting. In this expression of the interaction equation, Tu is the applied torsion at ultimate, Vu is the applied shear at ultimate, Tc is the capacity of concrete under pure torsion, Vc is the capacity of concrete under shear. Based on the interaction equation, the reduced capacity of concrete to resist torsion, which is denoted as Tc1, is given below. Tc1 is equal to Tc times E divided by E plus Ec. We shall define these variables E and Ec. The code recommends to limit Tc1 to half of the ultimate torsional moment. Thus, the concrete should not carry more than half of the torsional moment that comes in a beam. The parameters E and Ec are the ratios of torsion and shear demands at ultimate and concrete's capacities respectively. Thus, E is the ratio of Tu divided by Vu, which is the ratios of the torsion and shear demands at ultimate, and EC is the ratio of the concrete capacity to resist torsion and the concrete capacity to resist shear. These are the two variables which are used to write the expressions of the capacities of concrete to resist torsion and shear in a compact way. The reduced capacity of concrete to resist shear is given below, where Vc1 is equal to Vc times Ec divided by E plus Ec. Again, this equation has been derived from the interaction equation of the torsion and shear. To come back to the design of transverse reinforcement, the transverse reinforcement is provided in the form of closed stirrups enclosing the corner longitudinal bars. This is a very important requirement for the design for torsion. The torsion generates a circulatory shear, and hence the stirrups need to be closed in order to resist the circulatory shear. An open stirrup is not adequate for torsional resistance. The closed stirrups have to be held in place by longitudinal bars at the corner, and the detailing requirements we shall come in the next module. The amount of transverse reinforcement ASV is equal to the higher value determined from two expressions. The first expression is based on the Skewbending theory. ASV is given in terms of the equivalent moment generated due to torsion, which is denoted as MT. ASV is equal to MT times SV divided by 1.5 B1 D1 Fy. In this expression, B1 is the distance between the corner longitudinal bars along the short side, and D1 is the distance between the corner longitudinal bars along the long side. Thus, for a rectangular section, B1 is the shorter distance between the longitudinal bars, and D1 is the larger distance between the longitudinal bars. MT is the additional bending moment from torsion, whose expression we had seen during mode 1 failure. SV is the spacing of the stirrups. Fy is the characteristic yield stress of the stirrups. The grade of steel for stirrups should be restricted to Fe 415 or lower to have adequate ductility in the stirrups. Thus, we have found one expression of the transverse reinforcement, which is in terms of the equivalent moment due to torsion, and this is derived from the Skewbending theory. The second expression is based on a total shear requirement, and it is given as ASV is equal to AV plus 2 times AT. The first component, AV, corresponds to the flexural shear to be carried by the stirrups, which we can calculate from conventional shear design. The second component, AT, corresponds to the torsional shear to be carried by the stirrups. The factor 2 in front of AT considers that the torsional shear is additive to flexural shear in both the legs. Let us try to understand this equation for different types of sections. The following sketch shows the addition of flexural and torsional shear for a hollow section. Due to the flexural shear, there is vertically downwards shear occurring in both the legs of the hollow section, whereas due to torsion, there is a vertically downward shear in the left web and vertically upward shear in the right web. Thus, when both shear and torsion are occurring, then the left web will see a higher shear as compared to the value generated from VU, and the right web will observe a lower shear compared to the value generated due to VU. But the code neglects the subtractive component. The two shears are additive in the left web, whereas they are subtractive in the right web. Since the stirrups have equal areas in the two legs, the torsional shear is considered additive to flexural shear in both the legs. In the expression ASV is equal to AV plus 2 times AT, the assumption is that we are assuming that torsional shear is additive to flexural shear in both the webs of a hollow section. This is necessary because we are providing same area of the torsional reinforcement in the two webs of the hollow section. In solid sections, the two shears are not additive throughout the web. The flexural shear is distributed, whereas the torsional shear is restricted in the shear flow zone. What we see on the left hand side is that the flexural shear is distributed and acts downwards in the web, whereas the torsional shear is restricted in the peripheral shear flow zone. In one side it acts downwards, in the other side it acts upwards. In the central region, the shear is insignificant due to torsion. Thus, when the shear and torsion act together, they are not additive throughout the width of the web. Thus, for solid sections, the expression of ASV is conservative. If the breadth of the web is large, the two shears can be designed separately. The stirrups for flexural shear can be distributed throughout the interior of the web. For torsional shear, closed stirrups can be provided in the peripheral shear flow zone. This is adopted to avoid the clustering of the transverse reinforcement, that we are dividing the transverse reinforcement for shear and torsion. The shear reinforcement is distributed in the web, whereas the torsional reinforcement is provided as a closed loop in the peripheral region. Otherwise, we can design only closed stirrups to take both shear and torsion. In that case, we shall use the expression of the code that ASV is equal to AV plus 2 times AT. This expression is of course conservative for a solid section. The expressions of AV and AT are derived from the truss analogy for the ultimate limit state. AV is calculated from the shear that will be generated in the stirrups. It is given as VU minus VC1. VU is the shear demand, VC1 is the concrete capacity. When we subtract the concrete capacity from the shear demand, that is the demand for the steel stirrups, and AV is equal to VU minus VC1 times SV divided by 0.87 Fy D1, where D1 is the larger depth of the between the longitudinal bars. This expression of AV is developed based on a truss analogy for shear. the expression for AT is equal to Tu minus Tc1 times Sv divided by 0.87 Fy B1 D1. Tu is the shear torsion demand, Tc1 is the capacity of concrete to resist torsion, Tu minus Tc1 is the torsion to be resisted by the transverse steel, and that times Sv divided by 0.87 Fy times B1 times D1 gives the amount of steel required for the shear generated due to torsion. This expression is derived from the concept of a space stress analogy for torsion. Thus, once we know AV and AT, we are combining them to get the value of ASV, which is provided in the form of a closed stirrups. Otherwise, for a solid section, we can design AV separately and AT separately. The transverse steel should satisfy a minimum requirement. The minimum amount of transverse reinforcement is same as that for shear and is given by the following equation: ASV divided by BSV is equal to 0.4 divided by 0.87 Fy. This equation considers a minimum stress in the transverse reinforcement, which is equal to 0.4 Newton per millimeter square. Thus, the minimum amount of transverse reinforcement needs to be provided such that we avoid any diagonal tension failure due to the combined effect of torsion and shear. In today's lecture, we first studied the background for the design equations for the limit state of collapse for torsion. What we have understood is that we have identified 3 modes of failure for a beam under combined flexure and torsion. Corresponding to each mode of failure, we are defining an equivalent ultimate bending moment, and we are designing the steel for each of those equivalent ultimate bending moments. In the mode 1 failure, the equivalent ultimate moment acts in the same direction as that of the flexural moment, but the magnitude of the equivalent moment is higher than that for the flexural moment. We design the steel for the equivalent moment, which is given as ME1. If the torsional effect is large, which is measured as MT greater than MU, in that case we should also design for the transverse bending and negative bending. The transverse bending is modeled by the expression ME3, and for that there is compression in one side and tension in the other side face. The designed steel is for one side face, and we provide a symmetric amount of steel in the other side face. For the negative bending moment, we are designing for the top steel, and here the equivalent moment ME2 acts in an opposite sense to that of the flexural moment. Thus, if the flexural moment causes compression at the top, then the equivalent moment will cause compression at the bottom, and we are designing for the steel at the top. Now, this expressions of equivalent bending moment has been developed based on the Skewbending theory, and the expressions are used to design the longitudinal reinforcement. We had moved into the design of longitudinal reinforcement based on these expressions of the equivalent moment, and what we have found that the general design principle for a flexure is applicable for a member under flexure and torsion. The difference is that we are now considering equivalent bending moments instead of just the flexural moment. We have to satisfy the development length requirements as per the flexural design. Next, we moved on to the design of the transverse reinforcement, and there what we have found that the area of transverse reinforcement is calculated based on two concepts. Whichever gives the higher value is selected. The first expression is based on the Skewbending theory. The expression is related with the equivalent torsional moment mt, and from that we calculate one value of ASV. The second value of ASV is calculated from the requirement of total shear, that ASV is equal to AV plus 2 times AT, where AV is calculated from the direct shear requirement, the flexural shear requirement, and AT is calculated based on the torsional shear requirement. The two requirements are considered to be additive in the expression ASV is equal to AV plus 2 times AT. Now, before we design the transverse reinforcement, we should know the capacity of concrete to resist torsion and shear. Now, what we have found is that the capacity of concrete gets reduced in presence of torsion and shear acting together. When concrete is under pure torsion, the capacity is given as Tc is equal to Tcr, which is the moment generating the torsional cracks, and this expression of Tcr is derived from the plastic theory of torsion, and in that theory the maximum stress in the mid depth of the longitudinal side, long side, is equated to a tensile strength of concrete, from which we derive the expression for Tcr, and that is equated to Tc. For a flange section, we consider the section as a compound section, which is a summation of rectangular sections, and Tc is given as a summation of the capacities of the individual rectangles. In presence of pre-stressing force, the capacity of concrete is increased by a factor lambda p, which is a function of FCP, the average pre-stress at the level of CGC of the section. Thus, we take advantage of the pre-stressing force in the capacity of concrete to resist torsion. Next, we had recollected the capacity of concrete to resist shear. There are two expressions. One is for an uncracked section and the other is for a cracked section. Vc0 is for an uncracked section, which is derived based on the shear that generates a web shear crack. Vcr is for the cracked section, which is the shear which generates a flexural shear crack, and whichever is lower is taken as the value of Vc. Once we know Tc and Vc, we are considering a reduced capacity of concrete to resist torsion and a reduced capacity of the concrete to resist shear, and this expression is based on the interaction equation, which is a linear interaction equation for shear and torsion acting together. Once we know the capacity of concrete, we can deduct that from the torsion and from the shear, from which we can calculate the forces to be carried by the steel. And from this, based on the truss analogy, we derive expressions of AV and AT. Thus, we get the amount of transverse reinforcement that is needed for the torsion design. Next class, we are looking into the design steps. Thank you.